And it's running. And today we're going to do our first steps in forcing. But just before we start, I would like to remind you that today is a very special day in set theory. Oops, where are we now? Okay, let's go all the way to the top. Who cares? Okay, that's not really the best thing. But on the 29th of November, a couple of years ago, 1873, as you can see, Georg Cantor wrote a letter to Richard Dedekind, and with a very auspicious question. Namely, the question was whether the natural numbers and the real numbers could be brought into bijection with each other. And that is how set theory started. I just wanted to share that moment with you. Next week is another important day, but that won't be Monday, that won't be Tuesday. That's when Cantor wrote to Dedekind with an answer to his question. Okay, now I completely messed up my pieces of paper, but I think I'll get to we'll get it straight eventually. So what are we going to do today? Well, let me first recapitulate what we did last week.
By the way, we have a question in the chat. Where's the quote from?
Pardon?
Where is the quote from? Someone asks.
It's from a letter from Cantor to Dedekind.
Yeah, but which book can we find it from? Like which book?
It's, there is a book edited by, I think, Emmy Noether and somebody else, I forgot the name, of letters from Cantor to Dedekind and back. I made a scan of the whole page of the book, and I will put it on the ELO, but I think many libraries will have a copy of that. So it's something like the Briefwechsel Cantor Dedekinds or something like that. It's in German. Okay, and Robert already found a link. Very good. Alrighty, so let's get going. What did we do last week? Last week we tried to explain to each other why we could get away with countable, shall we say, models of set theory that's, well, not models of full set theory, but models of finite sets of axioms, and then try to make sure that some of those models do not satisfy the continuum hypothesis or do satisfy the continuum hypothesis. That was the strategy for getting our consistency results. And so what did we do? We wrote out, we took a finite set of axioms. Step one, we defined what it means to relativize those statements to sets. And then we said, oh, but we can find a beta such that all the formulas are valid in V beta. And some of those formulas are of the form for every x there is a y. So we need V beta to be closed under, say, the implicit function that is there. Next step, the next step was to use the Leuwenheim's column theorem from model theory and say, but wait a minute, if you have a set that satisfies some of your formulas and the language that you're speaking is not very big, we can actually find a countable subset of V beta that satisfies the formulas as well, that is also closed under those implicit functions and everything. And then we could take the Mostovsky collapse of that, which is a very heavy-handed way of saying we make the thing transitive. We find an isomorphic copy of A that is transitive. That also satisfies those formulas. And the thing we did, we say, okay, we take finitely many axioms, but for once and for all, we include in that family extensionality, pairing, union, power set. What else was there? Infinity. And regularity. Why? Well, those are just simple sentences, and we can add them to our finite list, and it won't destroy the finiteness of the list. What is really important in those finite lists, those will be instances of separation and instances of replacement. That's where we get the infinitely many actions from. So now get M to satisfy, say, not CH. That is our next goal. Fine. And what does that mean then for us? It means that those finitely many axioms that we picked are not strong enough to prove the negation of the continuum hypothesis. And then we, in the meta, on our meta level, will tell to each other, you see, there is no proof. Take any possible proof of CH, go through the list, look at all the axioms that are being used in the proof. Oh, that's a finite set. Oh, but wait a minute, there is a structure that satisfies those finite set, and it satisfies not CH. There must be something wrong with the proof. Okay, that is the general idea. But now we need to do something to our countable M to make it satisfy not CH. What we will do, we extend M, well, to the next letter, N. N will also be a countable transitive model for the finitely many axioms. We want to make M a little bit bigger. That's the only way we can actually get around this. We want to make M a little bit bigger and to a countable model N. That countable model N satisfies our original set of axioms, and it also satisfies the negation of the continuum hypothesis, again relativized to N. And that will be the end of the proof of the non-provability of the continuum hypothesis. Okay, how? Well, we're going to be cheating a little bit. We simply assume that our model satisfies all the actions of the set of C. That's just to make life a little bit easier and show that M will also satisfy all the actions of ZFC. So we will show how to show that all the actions of ZFC are satisfied. And of course, and I may think, yeah, but wait a minute, we cannot assume that M satisfies ZFC and so on. Okay, if you want to convert this to a proof in the way that we sketched it last week, you can say check the bookkeeping, so you can audit the proof. And well, simply quote unquote check which axioms you need to get, well, the phi1n up to phi kn, and because it will turn out that if we want to get a bunch of axioms in N, we want them to hold in N, and also the negation of the continuum hypothesis, we will need a slightly bigger set of axioms to hold in N. That's the only, well, not really a complication, but it's the extra work that we need to do. We will need M to be a little bit stronger than N, so to speak. It will need to have a bit more actions. But all of this could, in principle, be done sort of automatically. You look at what you use, and you simply put that in a list. And then at the end you say, but now we do the official thing with this finite list. Okay, what does M look like? Well, M is transitive. It is kind of a model of ZFC. So it looks like V. It has an ordinal spine. The real omega is in there because M is a countable transitive model, among others, of the infinity action. And omega can be described in a delta zero formula. See last week. Oh, but delta zero formula means no matter how you interpret it in a transitive set, you always get the same thing. You get the real, honest to God, omega. Now, all the ordinals are countable. There is a countable ordinal that, as far as M is concerned, acts like omega 1. And somewhat higher up, there is something bigger called omega 2. At least M thinks it's omega 2. What do I mean by M thinks? This is a theorem of ZFC. There is a smallest ordinal with no bijection to omega. The axioms that we needed to prove this, we put in our list. So that means that if M satisfies those axioms, it also satisfies this consequence. So there must be an ordinal, there must be a first one with this property that alpha is what omega 1 thinks, what M thinks is omega 1. Likewise, again, a finite list of axioms, there must be there must be a beta that is. There must be a beta that acts like omega 2, the smallest ordinal such that there is no bijection between beta and alpha. And you can make many more of those. So just to write it down, omega 1 M is the minimum alpha in omega with the property that for every F in M, have a function, we can write that in a delta zero formula, by the way. Domain of F is omega, that's the real thing. And all we want is that F is not onto alpha. So we say, well, alpha is not a subset of the range of F. There is a thing like that in M. We can prove that there is such a thing. Therefore, there must be an alpha in M with this particular property. And we relativize the whole thing to M by restricting this quantifier to M. Now, you can write down a definition for omega 2 as well. Now, last week, in the group interaction, at the very end, there was a question about the power set of omega. When you build the V beta, the real power set of omega was in that V beta. The Leuvenham-Skolem theorem picks out anything that is really definable. So P omega is going to be an element of that countable set A as well. The countable set we had on the previous page, we went from V beta to A. But P omega is definitely not an element of M. Why not? Well, M is transitive. If P omega were a member, all elements of P omega would be in M, but P omega really is uncountable. So it cannot be an element of M. So M satisfies the power set axiom. Omega is a member of M. There must be something that acts like the power set of omega in M. Well, it just so happens that if you intersect the power set of omega with M, you only look at the subsets of omega that are in M, then you get something in M. Why is that? Well, this, remember we had this mapping pi from A to M. We get this, and it turns out that this is just why is that? Well, for all the members of X, the members of X are natural numbers, and for natural numbers, pi of n is just n, and that means that pi of x is just x again. So this is, because when we take these are all the subsets of m that will belong to, subsets of omega that will belong to n. And so this is what we get when we say we need a power set of omega. What is the power set of omega in M? That's this thing. We relativize the power set to M, but we can actually calculate it. We get the power set of omega intersected M. Okay, that's good to know, because now we can sort of get an idea how to destroy the continuum hypothesis, so to speak. We extend M. Okay, what are we going to do? Here is our picture of M again. What are we going to do? Well, we're going to extend M horizontally. It almost sounds like, it feels like a field extension, if you've seen that in algebra. Remember, in algebra, you take a solution of a polynomial and you adjoin it to the field, and you get a bigger field, and that is the field extension. We're going to do something quite similar. We will make sure that the ordinals don't change. In and of itself, that's not really important. We want to extend M so that we get the negation of the continuum hypothesis. But for practical purposes and technical purposes, it's quite useful to know that the ordinals in N and the ordinals in M are exactly the same collection. So we're going to make sure that that's going to happen. So how do we get not CH? Well, make an injection. We want to make an injection from omega to M into the power set of omega, but then in the extension, except we don't have the extension yet. So maybe for the moment, we have P omega, we want to add a few elements of P omega maybe to M to get our injective map. We're going to assume, we may as well assume that this continuum hypothesis holds in M, because if it doesn't, then we're already done. We only need to take some action if the continuum hypothesis does not hold in M. All right. Okay, the injection we call F. Well, F cannot be in M, obviously. So F comes from the outside. All right. And we add it to M. Okay, easy enough. We see many such F. We have a tiny countable universe that plays set theory, and it has a thing that it calls omega 2, and we know, oh, that's omega 2 of M. We know it's a countable ordinal. We have an uncountable power set of omega at our disposal. So no problem whatsoever to pick an F like this. Just take one. And do a kind of a field extension. How would you make that field extension? Well, you could, for example, take a V beta that's quite big. Remember, we had the countable the countable structure A, which was sitting inside of V beta. Okay, with a bit of luck, we can take the F. Well, the F we can take in V beta because all the Fs that we could worry about are quite low in the hierarchy. Do the Löwenheim's column thing. And do the Mostovsky thing. Simply repeat what we did last week, but start with this countable set. And we find a countable set that satisfies all the actions that we had. And we do the Mostovsky collapse, and there is our M. And because M is transitive, we will get M back as well. I'm not going to go through the details of this because, well, what could possibly go wrong? What could possibly go wrong with this? And when I pose the question like this, you're thinking right now, okay, many things can go wrong. Well, we could be quite careless. Our F could be a bijection between omega 2m and the power set of omega in M. Why not? We see from the outside that both sets are countably infinite. So why not take a bijection between the two? And then that makes life easy because now we have omega 2 many subsets of omega. So we know what continuum is going to be. It's going to be omega 2. Well, not quite, because Cantor-Bernstein now tells us also bijection we also get a bijection between omega 2 and omega 1, especially since we assumed CH in M. There was a bijection between omega 1 and that power set already. And now we have a bijection between omega 1 and omega 2. Bummer. omega 2 of m is not the omega 2 of n. There is a bijection between omega 2 of m and omega 1 of m. Omega 2 is no longer the smallest ordinal that does not have a bijection with that omega 1 of m. We lost the cardinal. So we have no idea whether the continuum hypothesis holds or not in n. All we did was get rid of a cardinal. Maybe the omega 3 of m is now the omega 2 of m, but we didn't do anything for that cardinal at all. Well, could even be worse. We could restrict f to omega . Why not? You know, we know p omega, pm of omega is countable, and we could take a very careless bijection that already, we could take another map from omega 2 to the power set of omega and already have a bijection from omega to that. And the rest of the map would be immaterial. Really bad. Well, the range, well, suppose that we add completely new subsets of omega to the power set of omega from n. We really add new things to that power set from the outside, stick them in there. Well, it could contain ugly subsets of omega. How ugly? Well, you and I know that m is countable. So you and I know that the set of ordinals that are in m let's call it delta, it's a countable ordinal. Ooh, one of those sets could code a well order of type delta. One of those sets could code a well order of omega in type delta. How? Well, we have a nice bijection between omega and its square, and we can take a subset here, let's call it x, and the bijection could turn it into an x prime, and that could be the well order. You see, when we say that our structure satisfies many axioms of ZFC, there is also the axiom that helps us prove that that we have very nice bijections between omega and omega cross omega. And as soon as we have that, every subset gets transformed into a subset of omega cross omega. And suddenly we have to worry about subsets of omega that under that bijection suddenly become strange well orders or anything. We need to avoid those, because if we get a well order of type delta, the whole universe collapses and we have nothing anymore. So really, so what did I do up to now? I said, well, we have a structure. It mimics the universe of set theory. We want to extend it. And what I've just showed you right now, sort of loosely, but is that you have to be careful when you add something to a model of set theory. Before you know it, you destroy your whole universe. So it has to be done with care. We need to build the F with care, with lots of care. We cannot just pick any old F and stick it on an M, because then all kinds of bad things can happen, as we have seen. So how? We must involve M much more. Well, we didn't involve M at all, except we wanted to take something outside of M. We're going to involve M. The mapping F that we build will be quite closely related to the model M. And all those bad things that I just sketched, they will not happen. It will take some work, but so we must involve M much more. Well, how do we do that? Well, many ways. We use Cohen's method. Well, actually, we don't really use Cohen's original method because that is quite difficult to read. But it was reformulated a few years later by another logician called Schoenfield. He sort of cleaned up the presentation a little bit, and that is the type of presentation that we will be using today and the next few weeks. We use finite approximations. We're going to approximate that F using finite bits and pieces of information. And what are those finite bits and pieces of information? Well, these. We are going to use a whole set, and I'm going to call it P, but sort of the better notation for it will be this. But there's a whole mouthful, so I abbreviate it with P. What is this? Is the set, it's a set of little p's where what? P is a function. Okay, fair enough. The domain of P is a finite subset of what? Well, omega 2 cross omega. So that's the same omega 2 cross omega that you will see within the Fn. And the range of P P takes only the values 0 and 1. Of course, better we do this in M. So we should actually say PM. Okay, this P is the one that we talk about. It uses our omega-2, but whatever we prove about it also holds for the elements of P for which the domain if you were to write down the definition of this P, and you would replace every quantifier needed in that definition by M, you would end up with this set. Should be a function. Well, that is delta 0. The domain should be a finite set. Well, that's not quite delta 0, but if there is a projection between you and a natural number, that natural number is unique, and that makes it absolute. So the domain should be a finite subset of omega cross omega, and that is where the quantifier M comes in. When you relativize to M, you say the domain should be a finite subset of omega to M cross omega. That the range is a subset of 2 is no restriction because 2 is a subset of M already. So when you do forcing, you sort of jump back and forth between M and the real world because working in the real world feels a little bit easier. But when you've done a bit of work, you say, okay, relativize to M, and then you can draw your conclusions. What is the, oh, now here is the picture of Cantor's letter. I'll fix this later. What's the interpretation? And once we have the interpretation, we'll have a short break. How do we get F? Well, if P is in P and alpha n is in the domain of P, then P tells us what does P tell us? Well, it tells us that n is going to be a member of F alpha This is the information that the finite function carries about the function f that we are about to construct. If our ground model M satisfies CH, as we implicitly assume, then there is no injective f from omega to M to the power set of omega in M, because then we would get a projection between omega 2 and omega 1, and that is impossible. So these P's, these finite functions, they contain information about, shall we say, an imaginary function f from omega 2m to, well, the power set of omega in a slightly bigger universe. And what does P tell us about it? Well, it tells us a little bit about what is going to be inside f of alpha and what is going to be outside f of alpha, as long as, of course, if alpha comma n belongs to the domain of P. Okay, think about that for a moment. then we'll have a break. It's 10 to 3. So 5 past 3 will continue. And so question is, and you may think about this, how to combine these finite things into one big F. Because that is what we'll be trying to do in the next 2 hours. Combine those little bits and pieces into one big F, and that big F should be an injection from omega 2 into the power set of omega. Okay, we'll do that in 15 minutes, and now I want to pause the recording. Off we go. Yep. And so the question now is, we have this thing that consists of all kinds of finite approximations to this big F, and we want to combine these into one big function F. Well, we cannot combine everything. First, we do some notation. Okay, in the forcing terminology, we order our functions in this case. When we will do it in general, we will talk about partial orders, and partial orders will usually be written by less than or equal. And our functions are partially ordered by inclusion. But in the forcing terminology, the larger function is smaller because we call a smaller condition stronger because it narrows the number of possibilities. If the function is bigger, then there are fewer possibilities to define the big function f, because the p narrows down, it gives more information, so it narrows down further possibilities. P restricts more. That's all, I think, reasons after the fact for deciding on the less than or equal. We could also do bigger than or equal. That would be the Israel convention, but I like the less than or equal convention for the stronger thing more. So occasionally you have to turn an order upside down, but that's not too bad. We cannot take if we take that two functions p and q, and we have some alpha comma n in their domains, if we have two functions that have a point in their domain where they differ in value, then we cannot use them both. Definitely one of P or Q cannot be used to build our future F, because we would be left with a non-decision about N being an element of F alpha or not. We really want to know whether n belongs to f alpha. In that case, if we want it to be in there, we should be using p. If we don't like it to be in there, we should be using q, but we cannot use p and q simultaneously. We say that p and q are incompatible. And the notation that I personally use lots is sort of p and q are perpendicular. I use the perp symbol from LaTeX. And otherwise compatible. So if they are compatible, it means compatible means so two partial functions go together well if their union is still a function. And if their union is not a function, then they're incompatible, and we write p perpendicular to q. Okay, so we built f by taking a suitable set, a suitable subset, and let's call it G of P. And how do we build F out of that suitable subset of G? So that suitable subset G, well, we want the union of all those functions that we put, all those finite functions that we put in G, when we union them up, we want that to be a function. We don't ever want two incompatible elements in G. So if P and Q are in G, then we want P union Q to be in G as well, because we want them to be compatible. And if they contribute to G, then we simply demand that their union is in G as well. So if we want the thing to be a function, then this should be a demand on our G. What else do we want of our G? Well, we want it to be a complete function because we want to build our F. Our F should assign to every ordinal a subset of omega. Well, every natural number should be decided whether it's going to be in that subset of omega or not, because we want F alpha to be F alpha to be what we promised. We said a finite function will tell us a little bit about finitely many F alphas and finitely many natural numbers. We want the information that P gave us, we want it to be used, and we want F alpha to be exactly this. Well, but that means that the domain of that union of G should be that whole rectangle. Okay, fine. What else do we want? Well, we want F alpha, we want F to be an injective map. That means that if alpha is not equal to beta, then we want F alpha to be different from beta. That is, we want some n in the symmetric difference of alpha and beta. It should be in F alpha but not in F beta, or in F beta but not in F alpha. And how do we get this? We get this by having that, when we take that big function, that union of G, and we evaluate it in alpha comma n, and we evaluate it in beta comma n, we simply want the values to be distinct. Whether one is 0 and the other 1, or one is 1 and the other 0, that doesn't matter, as long as they're distinct. Okay, and how do we get this? Well, we want a PNG that does this. And we're going to get one because the value at alpha comma n is decided by a P, the value at beta comma n is decided by a Q, and the P and the Q are compatible, so their union will be one function that does this. So we want P and G and n in omega such that okay, we want one P already to decide that for us. Okay, fine. Now, that first demand that we wrote down, that the union of two elements is again in G, that is quite important, and we'll put this in a definition. We'll make it slightly more general. We want G to be a filter. Now, some of you may know filters from topology, or a bit of set theory, or even logic in the building of models. You can extend the notion of filter to be also something in partial orders. What do we want? We write it slightly more general than what we had above, but it's equivalent to what we had above. If there is a function that contains P and Q, then the union of P and Q sits in that function and is itself a function. But in later developments, this is the definition of filter that we're going to be using. And of course, for every P and G, for every Q which is bigger than or equal to G, we want Q to be in G as well. Any finite function that is already in G, every subfunction of that is going to be in G as well, and this should have been a P, of course. This is what we want G to be. If G is a filter, then the union of G is definitely a function. Okay, we wanted domain of that union of G to be omega 2 cross omega. How do we do that? Well, we can simply say, well, we want the domain to be that, but we're going to do it indirectly. We define d alpha n to be all the p's in P with the property that alpha comma n is in the domain of P. And so to get this, our demand is going to be this is a very complicated way of saying that we want alpha comma n to be in the domain of some P that is a member of G. But this is the way that we'll be talking about much of the forcing business next week and in the final 2 weeks as well. Why is this? Well, d alpha n is dense in P. Well, that sounds very impressive, but I haven't defined it. It means that for every P in P, there is a Q in d alpha n such that Q is stronger than P. This is what dense means in our context. A subset of a partial order is dense if it satisfies this formula. Why is it dense? Well, easy enough. P is fine. Take P in P. Okay. If alpha comma n is not in the domain of P, if, okay, case one. Case one, alpha comma n is already in the domain of P, we're done. Case two, it is not. Well, say Q is P union, okay, and this is going to be okay, this kind of thing you write to impress outsiders. This is a function. Look closely. It's a set of ordered pairs, P, and here is another ordered pair, and the first coordinate of that ordered pair is itself an ordered pair. It's alpha comma n, and the second coordinate is 0. So we have extended the function P to a function Q, and that function belongs to d alpha n because alpha comma n is in its domain. So yes, d alpha n satisfies this particular formula because Q really is a larger function than P. Okay, so if we make sure that G intersects all those d alpha n's, then we get a full function on omega n cross omega, and we can define our function f. We want f injective. And how did we make sure, how did we make f injective? Where was it? Well, we needed to make sure that this was going to happen. Given an alpha and a beta, we wanted at least one n such that this was going to happen. Oh, well, here we go. We can define another dense set, because this is where this is going. We'll be looking at dense sets in our P. here we write another set. It's all the p's with the property that we had up there. And so we want we want our G to intersect every one of those E alpha betas. Because if we do that, then we know that there is a P and we know that there is an N and so on. Also, E alpha beta is dense. And here is where we use the finiteness of the P. It looks like this sharing has stopped. My program quit, but somebody asked about the Israel notation. Yes, Israeli set theorists have the order in the forcing notation the other way around. They would say that a larger function is larger in the order. Okay, but now I have to reshare my screen. And I also want to and I needed to save my work, and I hope everything was saved. Yep, there we go. So I hope nothing goes wrong again. So where were we? We were going to make sure that the function f was injective. Fine. We have this set E alpha beta of p's, and we want to show that it is dense. So we take an arbitrary p. P is finite. Its domain is finite. There are only finitely many second coordinates to the members of its domain. Only finitely many natural numbers that occur in these ordered pairs. So we can even pick an n such that there is no gamma whatsoever for which gamma comma n belongs to the domain of P. Easy enough. Okay, now define Q is what? Well, it's P, and we do the same thing as a few moments ago. All right. And that was our goal. These are our demands on G. We want G to be a filter. We want G to be a filter. That's the first demand. We want G to intersect every one of those D alpha n's. And we want G to intersect every one of those E alpha betas. And how are we going to do this? Well, easier than you might think. M is countable. That's great, because now we know that we look at all the d alpha n's. We look at all those things that we wanted to intersect. That's a countable family, because now we, you and I, we step outside of M, and we say, we did our analysis, and we say, well, we need to intersect the d alpha n's, we need to intersect the e alpha betas. And now we say, well, wait a minute, our M is countable, and we only have countably many sets that we want to intersect anyway. And more importantly, those sets are dense. Here we go. Enumerate the family. And I'm going to show you that we can make very many G's. Take some P in P, I don't care, and build a sequence in P okay, by recursion, using the axiom of choice, and so on. The sequence is called Pn. And what does the sequence do? Well, P0 is less than or equal to P, and P0 belongs to D0. P1 is going to be less than or equal to P0, and P1 is going to belong to D1. That's possible because the sets are dense. If I have a member of P, I can find something in every one of those things that's below it. And so, well, now you see where this is going. The recursion theorem says us there is such a function. Okay, and G is going to be all the Q's in P with the property there is an N in omega such that Pn is less than or equal to Q. This is a filter. Why? Take two elements of G and take the largest of the two numbers that are used in the definition. So Q1 has P10 below it, and Q2 has P100 below it, but that means that both have P100 below it. So their union is below, so their union has still P100 below it. So the union belongs to the filter. And everything, if you have a function, then every subfunction belongs to G as well. That's also because of this condition. And we have made sure that Pn is in the intersection of G and Dn. And so we know that we have our two red conditions. G intersects every D alpha n, G intersects every E alpha beta. Even better, and I'll do this right away before I forget it. There's one thing that I almost forgot. These sets, when I'm restricting myself to the partial order in M, these sets belong to M. When I say I take all the elements of PM that have the certain property, then I get members of the universe M. And when I restrict my D alphas to M, they are going to be dense in the partial order PM. And so on. Because what I have proven, the proof can be copied in M, and we get the relativations of these things to M are dense as well. And so we could enumerate D, that's the family of all things in M, we could enumerate all the sets that are members of M, that are subsets of P, and that are dense in PM. That family, it consists of members of M. We can see it, we see it's countable. We don't really have to use only those countably many sets that we are really interested in. We could have said, take all the dense subsets of P that are members of M. M is countable, so there's countably many of them. And we could get G that intersects all of them. At no extra cost. The proof is just the same. Such a G, if we do that, is called M generic. And some people will say it's M generic on P or something, or words to that effect. The G cuts through all the dense subsets. It meets all the dense subsets of M, and the term that is being used for that is M generic. Okay, so there we are. We get G. I have shown you how to, well, how to choose G, and there is lots of variation in it. We can take any element P and make sure that it belongs to that particular G. So if we really want our family to adhere to the choices that the little function P already makes, we simply make sure that P is a member of the generic set, the generic filter. If we don't care, we don't, but if we want, we can do that. Which is an important thing that we will come back to next week. We get our G. The domain of G, the domain of the union of G is omega 2 M cross omega. The F that we make from G, well, let's call it F of G. It's an injection of omega 2 M into the power set of omega. It's not an arbitrary injection. It's one that we made relatively carefully by using those finite approximations and by using a very specific type of subset of those finite approximations. And the way we chose them is going to be important also in the next hour. Let's see. Where are my notes? Because I'm getting ahead of myself. I'm already, yeah. Okay, what we will see next time, but we take it on faith for now, because I want to show you that the essence of forcing is not so much what we've been doing, right? Well, part of what we've been doing is really important to forcing, but the way you do the work is largely just combinatorial. So next week, we will see how to make out of M and out of G a model of set theory that we will call N, Nicholas. It will be the smallest model that contains it'll be the smallest model of ZFC that contains M as a subset and G as an element. The way we make it is really straightforward. We just use a few set theoretic operations and that's it. But what we apply those set theoretic operations to, that's a different matter. Okay, let us believe this for the moment. And in a moment, I will ask you to believe one other thing. And once we have that, then will have reduced our problem to a problem in combinatorics. A problem that we already solved, and I will tell you that in a moment. So now the big question is, there are a few questions, but the big question, and there are all kinds of sub-questions. Okay, we have FG. So we have G, we have the F that we created from the G. And so the range of F of G will be a member of N because G is a member of N. F of G is constructed from G, that's a member of N. So if N is a model of ZFC, the range of G is a member of N. So F of G goes from omega 2m to the power set of omega in N. And it is injective. Lovely. So what do we need to do now? And that we will be doing in the next hour. Well, we need an injection from omega 2 of N Nicholas into the power set in N Nicholas of omega. We have an injection from omega 2 in M Mary into the power set of omega in N Nicholas. And what I have showed you in the first hour, if we take an arbitrary function, things could go wrong. We could introduce a bijection between omega 1 of M and omega 2 of M, and then omega 2 of M is no longer a cardinal. So what is our goal for the next hour? And I keep doing that. What do we need to show that no map if I take a map from omega to omega 1 m, but the map G belongs to n, and if I take a map from omega 1 m to omega 2 m, but the map is a member of n, can be surjective. Because if one of those two can be made to be surjective, we're in trouble. Because then we don't have a mapping from omega 2 of Nicholas into its power set. We want to make sure that there is no new mapping from omega to omega 1 that is surjective. There will be new mappings for sure, but we don't want any surjective mappings. And that is what we'll be doing in the next hour. This is a good moment to stop. So I'll pause the recording again. And then at about 4 o'clock, we'll
You're still muted, KP.
okay, so now we have sound and recording. So let's see how we can attack this problem. We have two situations. We have a map G from omega to omega 1 m. We have H from omega 1 m to omega 2 m. And we want to show in both cases that they're not surjective. How on earth can we do that? Well, we need a way of describing G and H, because we have, the way I wrote it down, G and H came out of nowhere. Well, we know they are in N, but that's about it. I haven't told you how to construct N from M and G, and I'm going to mention just a little bit of how that construction is going to work. So we have, the situation is this. We have X, we have two sets, X and Y in M. And we have a map, let's call it G, from X to Y. And G is a member of N. Okay, fine. Now, like I said, N is constructed from M and G. And how does that work? Well, in our case, we can be relatively explicit as to how that construction is going. G is, of course, a subset of X cross Y. It's a set of ordered pairs. And what we will see next week so you have to believe me for now. Next week, we will see the following. There is a relation, a subset, let's call it R. R is a subset of P cross x cross y. So this is a general fact. If you have a member of M and a new subset of that, you can represent it in the way that I'm going to describe now. If you have a relation and you have a subset of the domain, then you can write down this. This is just like taking images under functions. Now you're taking images under relations. You have relations between members of P and members of X cross Y. And everything in X cross Y that is related to something that happens to be in G, we collect, and we can make sure that this is just our function G. This is what I mean by we can construct the members of N from M and the generic filter G for subsets, for new subsets of old sets. This is how that construction is going to be. You take a relation even more, that relation is a subset of P cross X cross Y, but as we shall see, R is actually a member of M. And when we evaluate that relation in G, we get our thing G back. And we can also, and that is useful to have in many circumstances, for every M generic set H, this is not trivial. This is going to take some effort next week. But if we have a function in the new world, so to speak, then we can talk about that function inside M to some extent. We can find a member of M that happens to be a relation between members of P and members of that old subset, in this case, X plus Y. If we apply our generic filter to it, we get the function G back that we're talking about. But that relation is so special that no matter what generic filter we take, when we interpret the generic filters through the relation, we always get a function from X to Y. Okay, this, like I said, it's not trivial, but this is the thing that we're going to play with. All right, what can we say about R? Well, here is a thing we can say about R, and this is what's going to make things work for us. Suppose what? Suppose we have X in X and Y1 and Y2 in Y different. So we have two distinct members of Y, and assume P1 and P2 in P are such that well, P1, X, Y1 is in R, and P2, X, Y2 is in R. suppose this, well, this is eminently possible. So what does it mean? Well, it sort of means that P thinks that g of x is, P1 thinks that g of x is going to be y1. P2 thinks g of x is going to be y2. Well, that means that P1 and P2 are in disagreement. Then P1 and P2 are incompatible. You can feel this coming. If P1 and P2 were compatible, then g of g of x should be y1 and y2 at the same time, and it wouldn't be a function. But of course, this is talking about the g, and here is where we use that for every M generic set, R of H is a map from X to Y. Because assume P1 and P2 are compatible. Well, what did we do in the previous hour? We showed that no matter what element of P we think of, we can always stick it into a generic filter. Then P1 union P2 is an element of P. It is a function. Well, now you see where this is going. Take, and this is what we do from the outside of M. This we can do. Okay, lovely. But now thanks to this P1 and union P2, if we take the evaluation, we put an H here, we put P1, P2 here, and we find that X1, X comma Y1 and X comma Y2 are in RH. So RH is not a function. It's not a map. Contradiction. That's it. Suppose we have an X, suppose we have this, then the two things that think differently about the value of the function at X, they have to be incompatible. Okay. What can we do with this? Now, look at, take an X in X and put this. We take an X in X and we look at this particular set. What do we know? Well, we know G of X is going to be a member of I of X. Why is that? We put all possible Y's that we could ever have as a potential image of x into I of x. And so how do we know that g of x is in I of x? There is a p in g that has this particular property for g of x, because there is a p in g such that p comma x comma g of x belongs to R. I of x belongs to M. Why? Because y belongs to M, p belongs to M, R belongs to M. So it's a member of M. It's defined in terms of M. Suppose if we take for each y in I of x a py in P with px, no, not py, comma x, comma y in R. There must be one because y is in I of x. We use the axiom of choice a lot in this, in these arguments, as you can see. Then what? Py, y in I of x is pairwise incompatible. If I take a py1 and a py2, then I am in the situation of this lemma, shall we say. We have a y1 and a y2 in x, and we have an x here. This p1 could be our py1, and this p2 could be our pi y2. And we have just shown that means that those two will be incompatible no matter how I choose them. Okay? If you give me an x, I will construct the I of x using the axiom of choice. I will construct the family A of x consisting of py's y in x, and I get a pairwise incompatible thing. This is called an anti-chain. Because the things are definitely not comparable. They are completely incomparable. So they definitely form something that is sort of perpendicular to a chain in the partial order, an anti-chain. We prove in a moment each AX is countable. Hence, so is each IX. Because choosing PY to go with Y is definitely an injection. And so there. Okay. Now go back to our no, let me make this. So what does that mean? What do we know? We know oops, we know that g of x is a subset of this. And okay, this is in N, but this thing is constructed completely inside M. We made one existential statement. We said there is an R such that this happens. We will actually be able to prove the existence of the R independent of generic sets or whatever. We can simply prove the existence of the R in M. That sounds a bit weird, but we will do that next week. So we have a member of M, and everything we have constructed thus far from this R belongs to M, because we never went outside M to create anything that was related to the I-axis or the A-axis or whatsoever. This is something that happened in M. So cardinality of this in M the cardinality of this is at most that of x times L of 0, and x is usually infinite, so it is at most the cardinality of x. When we calculate the cardinality of that set in M, it is at most the cardinality of x times L of 0. Okay, but now we're done. We had a g from omega to omega 1 M. We assumed we had a mapping from omega, so the G is now back to being that assumed mapping from omega to omega 1. The range of G is countable. Why? Because it is contained in a countable union of countable sets. We had the H going from omega 1M to omega 2M. H of omega 1M is contained in a, oh, no, let's do that differently. It is contained in a subset, in a set that is a member of M, and in M, that set has cardinality Aleph 1. So H omega 1M is definitely not omega 2M. Both mappings cannot be surjective, and that is what we wanted to prove. Okay, so what do we need to prove? We need to prove that each, and that's the theorem that we will prove, every antichain in P is countable. This is the theorem that will finish the proof modulo, of course, all the developments of the extension. But if we believe that the extension will work, then this finishes the proof that the negation of the continuum hypothesis holds in N. Well, there we go. We take an antichain in P. So what do? We need to show that every anti-chain is countable. So of course we go the other way. We take an uncountable subset of P, and we're going to show that it's definitely not an anti-chain. We're going to find two elements of A that are compatible. Step one, we're going back to I think it was lecture 9, where we proved the delta system lemma. And I think I mentioned at that time, this is going to come back. Well, now it is coming back. The delta system lemma tells us what did the delta, I'll tell you what it says, because that is exactly what we need. There are two things: a fixed finite set X and an uncountable subset of A, and let's call it B, such that if P is distinct from Q in B, then the domain of P intersect domain of Q is equal to X. This is what the delta system lemma tells us, and I apply it to the set of domains of our functions. All right. So here is the situation. We get a set X that is fixed. And when we look at the members of B, then we have the domain of P, except, of course, for X. We have the domain of Q, except for X. We have the domain of R, except for X, and so on. So these bits are parts of the domains that are not common to everything. Outside of X, the domains of the P, Q, R, whatever, all the members of B are disjoint. Okay, how many functions do we have? Uncountably many. How big is X? X is finite. There are how many functions from X to 2? That's only finitely many. So there is one function, let's call it R from X to 2, and C in B uncountable, such that what? Well, when I take P, I restrict it to X, I get R for all P in C. I have uncountably many functions. I take the restrictions of those functions to X. There are only 2 to the X many possibilities. That means that one possibility, at least one possibility, is used uncountably often. Well, all pairs of elements of C are apparently compatible. Why is that? Well, take 2. Take a P and a Q from C. What does Q look like? Well, this is Q. On X, we know what the values of Q are. They're determined by the little r, and here are the other values of Q. And here is P, and we know what the values of P are. Well, on X, they do the same thing as what R does. And outside, we have the other values of P. The union of P and Q is a function, and so they're compatible. There we go. So let's recapitulate. We took functions from omega to omega 1m, or a function from omega 1m to omega 2m. We quoted the general result that a new subset of an old set can be created using a relation on the powers on the P cross that old set. And since the new set was a function, we could say something about the number of coordinates that we could have in that particular case. Countable, and that told us that the range of that new function in the case of domain omega was countable, and in the case of domain omega 1 had cardinality omega 1. In both cases, the thing was not surjective. But the important thing is, it depended on the cardinality of anti-chains in the set P. So we have provisionally, because we do have to fill in all kinds of details next week, in N, we do have an injection from its omega 2 in its power set of omega, and so N satisfies not CH. Well, there are many questions you can ask about this, but the first conclusion for us now is that we know that there is no formal proof of the continuum hypothesis. Take the formal proof, like I sketched last week. Take all the axioms that we need in that proof. Take a few more, as we will see next week, we need a few more to get a model M that satisfies those axioms and those few more. Use those few more and our axioms to show that we can build the N. That N satisfies our original axioms, that we can do, and it also satisfies not CH. So our N blocks a potential proof of the continuum hypothesis from axioms of ZFC. And since the method is completely general, this blocks every possible proof. So that's the thing that we have learned today, well, apart from all the details that have to be done next week. So we have a to-do list. We have to show how to make M of G out of M and G. We have to prove that those relations R actually exist. That's going to take some time. And we have to show that really the N that we get satisfies any one of the axioms that we really wanted to satisfy. That's a large job, and I hope that I'll be able to do that next week. one comment that I want to make here is related to something that I said last week. The trouble with forcing, or the problem with forcing, problems with forcing that you may have are twofold. One, model theoretic. You have to build models. You have to interpret your language in structures. You have to be able to do that. You have to get used to relativation. You have to make sure that you know what absoluteness means in order to jump back and forth between the real world and that tiny little countable structure that mimics your set theory. You have to be able to do that. But the other thing that you have to be able to do is simply combinatorics. Because what we did, we had a combinatorial problem in N. The combinatorial problem wasn't really difficult. It was to show that the range of a certain map wasn't the whole codomain. We translated, using the relation R and the generic filter, that problem to a combinatorial problem back in M. And then we had to solve the combinatorial problem. Well, luckily, I solved that combinatorial problem a few weeks ago when I proved the delta system lemma. And that is the other difficulty, if you will. If you want to apply forcing, you'd simply need to know every now and then quite non-trivial combinatorics. The problem in N can be translated back to a problem in M, but the problem in M might ask for lots of work. Okay, here we needed the delta system lemma. That was relatively easy given the stationary sets and the pressing down lemma that we had. But there will be things in future applications of forcing that you might encounter where you will need way more clever things for your construction to work. One thing that I think, it's 10 minutes, I think it's not going to work completely, but I do want to make a few remarks about that, and I think then we'll adjourn. I wrote it down in my notes, and I'll put my notes on the ELO so you can read what I also had in mind today, and I'll come back to that later. But what is 2 to the L of 0 in M? Well, it is, oh, damn. Okay, my editor stopped again, and I think I'll leave it at that. I'm not going to restart it again. I'll save the material and put it on the ELO in a moment. I'll just say what I wanted to write down. You can calculate the new value of continuum is going to be the old value in M of L of 2 to the power L of 0. Okay, you can deduce that from the notes that I'll put on the ELO. You can also calculate what 2 to the L of 1 is going to be. Now, if you assume in your starting model M that 2 to the L of 0 is L of 1 and 2 to the L of 1 is L of 2, then in our model N, you will get, and we will see that later on, that 2 to the L of 0 and 2 to the L of 1 are both equal to L of 2. That is something that many people have a problem with, but it's something that happens in set theory. We have two sets of completely different cardinalities, L of 1 and L of 2. L of 0 and L of 1, but by golly, they have the same number of subsets. That's not something that happens with finite sets, but with infinite sets, that's very well possible. The other thing is I put 2 links on the ELO on today's page. One is an article by Cohen where he discusses how he came to his forcing method. And in it, he also describes how he got to the countable models that we talked about. And it's more or less what we did, except in a slightly more naive fashion. The other thing that I put on the ELO is a translation of a chapter of a set theory book by 2 Czech mathematicians, Baltzar and Štěpánek. And that's where I stole the idea from of using relations in the ground model to describe new subsets of old sets. I'm not going to follow that chapter all the way, but it's worth collecting it, so to speak, for your own little library, because it shows you one way of approaching forcing that uses Boolean algebras, which is a very nice way of doing things, but it's not the way that we're going to be doing it. We're going to be following mostly Koenen's book. And the reason for that is that that's how I learned it. So that's the best way I can explain it. I'll leave it at that for today. And I'll stop the recording here. I want to stop the cloud recording.